It's Tuesday again, and I would like to hang with you lads, but I'm off to listen to the new episode of the Slaven Selection Show. Play now or stay in dark forever.
Finding the patient's underlying ailment or condition requires a diagnosis. In a similar manner, celestial trajectory diagnosis, if released in time, many stones from heaven can be placed in the appropriate box, relieving us of the anxiety that arises whenever we hear a seductive phrase like "something is coming this way" or that we are doomed. So yes, please do look up as often as you can. The history of meteor observation dates back centuries, with significant developments occurring in the 19th and the 20th centuries. Meteors have been witnessed by humans since antiquity, with detailed records found in Chinese, Japanese, and Korean archives. In 1798, Benzenberg and Brands conducted the first observing program designed to determine meteor heights. Johann Friedrich Benzenberg and Heinrich Wilhelm Brands were two German scientists who made significant contributions to the study of meteors in the late 18th and early 19th centuries. Their collaborative work laid important foundations for our understanding of meteors. They conducted a series of observations to ascertain the height and velocity of meteors, and both were fellow University of Göttingen students. They actually wrote together attempts to calculate the distance, speed, and course of meteors, which was the title of the paper. They presented their findings in 1800. The scientific understanding of meteors has advanced significantly as a result of this publication. And on December 14, 1801, over New England, a massive fireball was observed shooting across the sky, signifying a significant astronomical occurrence. The so-called Weston meteorite was the term given to this fireball as it broke apart and scattered over Weston, Connecticut. The incident was witnessed by numerous people, and witnesses from Fairfield County, Connecticut, all the way to southern Vermont reporting seeing it. They observed a crimson ball of fire over 2/3 the size of the full moon, 3 enormous explosions, and a rumbling sound. Professor James L. Kingsley and young Yale scholar Benjamin Silliman rushed to the scene to launch an investigation. They located the falls, collected pieces of meteorite, and talked to witnesses. Through Silliman's analysis of the meteorite, it was revolutionary to discover spherical grains or chondrules that are absent from earthly rocks. He announced his findings in the Connecticut Herald on December 29, 1807. Later, in March 1808, a new version, which included a chemical analysis, was submitted to the American Philosophical Society. Academic and amateur meteor astronomers started working together when amateur astronomer Denison Alston invited them to see the 1833 Leonid meteor storm. The British Association for the Advancement of Science founded the Luminous Meteor Committee in the 1860s, and it published extensive standards for meteor viewing. People's interest in meteors grew after the 1866 and 1868 Leonid storms that were observed in Europe and the United States. The advancement of photography allowed for accurate measurements of meteor velocity and determination of radiant. In the 1860s, Giovanni Schiaparelli discovered a connection between comet orbits and meteor showers. In the early 20th century, reliable data on shower and sporadic meteors were gathered using photography techniques. When radar was used for the first time to find ionized meteor tracks in the middle of the 20th century, there was a sudden explosion of observational data. Scientists were able to associate different comet apparitions with distinct strands in the late 20th century because of computer modeling of meteor stream dynamics. New information about the orbits and intensities of meteor debris has been made possible by the development of optical detection networks. Impacts from asteroids are inevitable. Asteroids have affected Earth. However, meteors and meteorites are not the same as asteroids. Meteors and an asteroid's differences mostly lie in their states and location rather than their sizes. These are the main differences, typically found in the asteroid belt between Mars and Jupiter. Though some can be found elsewhere in the solar system, asteroids are stony objects that orbit the Sun. They can have about 4 meters in diameter and enter Earth's atmosphere approximately once a year. Larger asteroids around 20 meters in diameter, capable of producing powerful airbursts, strike Earth. We all remember the first dashcam YouTube mega event from 2013, the phenomenal Chelyabinsk meteor, about 20 meters wide, which exploded over Russia with an airburst equivalent to 500 kilotons of TNT. In 2018, a small 2 to 5 meter asteroid called 2018 LA was detected and confirmed to impact Earth in southern Africa. In 2019, a large airburst occurred off the coast of Kamchatka, estimated to be from an asteroid 9 to 14 meters in diameter. The observable phenomena known as meteors are produced when a meteorite or small asteroid burns up when it approaches Earth's atmosphere, leaving behind a streak of light in the sky. As long as it is in space, an asteroid will always be an asteroid. An asteroid or meteorite turns into a meteor when it enters Earth's atmosphere and begins to burn. Although it has a role, size, again, is not the only distinction. Asteroids often have bigger diameters, ranging from 1 meter to roughly 1,000 kilometers. Asteroids are larger than meteorites. They can grow into meteors, but they are usually smaller, ranging from dust-sized particles to objects as large as 1 meter in diameter. Unless their trajectories change, asteroids will continue to orbit the Sun. A transient phenomenon in Earth's atmosphere are meteors. If any part of the object survives the atmospheric entry and reaches Earth's surface, it's then called a meteorite. An asteroid the size of an apartment building could destroy a small city, and an asteroid the size of a 20-story building could flatten a small nation. Impacts can produce dust clouds that block sunlight, potentially causing global temperature drops and having widespread ecological effects. Small meteors frequently burn up in the atmosphere before reaching the ground. These so-called NEOs, or near-Earth objects that might be dangerous, are aggressively sought for and tracked by NASA and other organizations. Out of an estimated of 25,000 NEOs, about 10,500 larger than 460 feet have been found as of June 2023. Researchers are working on methods to identify and possibly divert potentially hazardous asteroids. And NASA's DART mission successfully proved how to change an asteroid's trajectory, raising the possibility that humans would eventually be able to deflect dangers. Well, first of all, it doesn't seem like there's a single organization like Man in Black that will take care of all of your space needs. Instead, it seems like the tasks and responsibilities are distributed among several agencies and/or detachments, which perplex me a little. Well, the following institutions and organizations monitor and assess the hazard posed by asteroids and meteors to Earth. There is a so-called PDCO, or the Planetary Defense Coordination Office of NASA. That's one example. In addition to coordinating efforts to develop technology and tactics to mitigate future impact dangers, this office is in charge of detecting, tracking, and characterizing near-Earth objects. Next, there is CNEOS, or the Center for Near-Earth Object Studies, a crucial part of NASA's PDCO, which calculates high-precision orbits for NEOs, forecasts their near-Earth approaches, and evaluates the likelihood of an impact. And of course, what we like to about today is GMN, or Global Meteor Network. GMN uses a global network of cameras and sensors, and there is a European Space Agency, also Planetary Defense Office, which monitors meteors that penetrate Earth's atmosphere and provides useful information on smaller meteorites. This office is responsible for identifying NEO situations, calculating impact likelihood, evaluating effects, notifying pertinent parties, and creating deflection techniques. Object Coordination Center, or NEOCC of ESA, Minor Planet Center, decentralizes emergency response agencies with impact risks, information, and NEO data. Then there is a National Nuclear Security Administration, or NNSA, which is a national security laboratories partnered with NASA to analyze potential asteroid impacts, characterize threats, and model early warnings and response capabilities. And also there's International Asteroid Warning Network. This global network facilitates the exchange of data and coordinates asteroid observations worldwide. Then Space Missions Planning Advisory Group. Then Canadian Space Agency, and which participated in NASA's asteroid impact exercises and is preparing to launch a satellite to search for potentially dangerous asteroids and comets. And the focus of the group is the development of the future deflection missions and technologies. The GMN and NASA's Planetary Defense Coordination Office are two organizations that monitor and study near-Earth objects, but they do so in different ways. The PDCO is in charge of identifying, tracking, and characterizing NEOs, which include comets and asteroids that approach Earth's orbit. It also organizes efforts to develop strategies and technologies to counteract potential impact threats, including initiatives like the Double Asteroid Redirection Test, or DART, which tests asteroid deflectors. As far as I can tell, they report everything to the Minor Planet Center, which serves as a global clearinghouse for near-Earth asteroids, under the supervision of the International Astronomical Union. The Small Planet Center, MPC, is the official organization for small planet observation and reporting. It is based at the Smithsonian Astrophysical Observatory and was founded in 1947. It is responsible for gathering observational data about minor planets, including asteroids, determining their orbits, and disseminating these data through the Minor Planet Circulars is called the Minor Planet Center. And the center was set up at the University of Cincinnati in 1947 under the direction of Paul Haggett. The Natural Satellites Ephemeris Service is an online service of the Minor Planet Center. The service provides ephemeris, orbital elements, and residual blocks for the outer irregular satellites of the giant planets. In contrast, the GMN is dedicated to tracking meteors and meteor showers. It is made up of a global network of sensors and cameras that monitor meteors as they enter Earth's atmosphere. The frequency and distribution of smaller space debris that burns up in the atmosphere are better understood by scientists thanks to this data, which advances our knowledge of NEOs and the concerns associated with their possible impacts. Although the Global Meteor Network and the Planetary Defense Coordination Office have separate main goals, their activity is complementary. The PDCO's wider efforts to track and describe larger NEOs can benefit from the excellent information the GMN gives on smaller meteorites. Both groups advance our knowledge of space objects that might be dangerous to Earth, which advances the overreaching objective of planetary defense. So to summarize, the GMN keeps an eye on smaller meteorites while NASA's PDCOs concentrate on larger NEOs and creating mitigation plans. When combined, they improve our capacity to identify and counteract possible cosmic dangers. It is very difficult to find meteorites and asteroids approaching the Sun for a number of reasons. Observing objects close to the Sun's direction with ground-based telescopes is challenging due to solar glare and brightness. Asteroids and other faint objects are overwhelmed and obscured by the strong sunshine. There is a little warning time when an asteroid approaches Earth from the Sun, since it is only briefly visible before it hits. The 2013 Chelyabinsk meteor was not seen in advance and originated from the direction of the Sun. When asteroids are near the Sun in the sky, it is more difficult to detect them from the ground because the Earth's atmosphere absorbs the infrared light that they release. Space organizations such as ESA are preparing missions as a NEOMIR, or Near-Earth Object Mission in the infrared, to orbit at the first Lagrange point, or L1, between Earth and the Sun in order to get around these constraints. From this position, NEOMIR is able to constantly observe the solar vicinity that is challenging to see from Earth. It can also find asteroids that are 65 feet or larger and traveling toward Earth from the direction of the Sun. By monitoring infrared wavelengths, you can provide any approaching asteroid at least 3 weeks' notice. Our current asteroid detection systems struggle to detect anything approaching from near the Sun's direction until it's too late. This early warning capability addresses a critical gap in those systems. Though the project's goal is similar to that of NASA's Global Fireball Observatory, it is actually inspired by it and concentrates on fainter meteors rather than only brilliant fireballs. In order to assist in the recovery of meteorites with known orbits, the GFO is an international network of all-sky cameras designed to identify and triangulate fireball meteors. The main objective of the Global Fireball Observatory is to track fireball trajectories and determine their orbits in order to retrieve related meteorites for scientific research. Its goal is to establish a planetary-scale observational facility to systematically search for brilliant fireballs in the night sky. Initiated in 2017, GFO is an international cooperation headed by academics from NASA and Australia's Curtin University. It deploys camera networks throughout the world in collaboration with the SETI Institute and other organizations. The Desert Fireball Network is one of the fireball networks that the project works with and is inspired by. Using an expanding global network of specialized all-sky camera systems, GFO continuously scans the sky. Fireball trajectories are triangulated by cameras in order to compute orbits and forecast meteorite fall positions. In the aftermath of fireball events, partners exchange data to facilitate meteorite recovery efforts. In a similar manner, the GMN is actually a citizen science initiative that tracks and triangulates meteor activity in the atmosphere by utilizing a worldwide network of camera systems. It finds and monitors much smaller fireballs and meteorites, usually a few meters in size, that have already reached Earth's atmosphere. By describing the flux of smaller objects that alone presents little hazard but may inflict localized damage upon atmospheric entry, the GMN data augments other NEO surveys. The Global Meteor Network initiative is closely related to the University of Western Ontario, or Western University. Researchers at Western University in London, Ontario, Canada's Department of Physics and Astronomy oversee the GMN. The GMN website is globalmeteornetwork.org and is hosted by the university and offers project-related tools, resources, and information. The project is headed by academics like Peter Brown, who is crucial to the analysis of the data that is gathered globally by the GMN cameras. Western University also oversees the GMN Outreach Project, which aims to involve students and citizen scientists in the field. For schools and groups to take part in the Global Meteor Tracking Network, it offers free camera equipment. But all of that began with my fellow countryman Denis Vida, who was motivated enough to build on the earlier efforts of the Croatian Meteor network, which Damir Šegon had founded some 12 years prior in order to establish the global Meteor network. After the CMN's early attempts, Vida got involved in developing RMS, or Raspberry Pi Meteor Station, a software that uses a Raspberry Pi for meteor detection, along with Dario Zubovic, another Croatian involved in the project. The article states that because the project looks so promising and the fact that most of the CMN ran on ancient computers that would have to be replaced as soon as possible, Damir got very excited and announced to CMN camera operators that there will be a Raspberry Pi solution by the end of the summer. Writing grant submissions is the last step in the long-term goals, which would allow for network expansion and the donation of Meteor systems to schools. The Global Meteor Network seeks to educate students about the glories of astronomy and STEM subjects while also bringing attention to the worldwide need for night sky surveillance. GMN is made up of more than 1,000 video meteor cameras that are hosted by experts and amateur astronomers in more than 45 countries worldwide. The open source software for video capture, compression, and meteor identification is installed on Raspberry Pi computers that are linked to the cameras. The primary objectives are to research meteor showers, detect brilliant fireballs to aid in meteorite recovery, and offer real-time data on the near-Earth meteorite environment. Every camera scans the night sky continually, looking for meteors within its field of vision. For analysis, the meteor data, orbits, trajectories, etc. is uploaded to central servers. Every day, the network posts the orbits of every meteor that has been seen in the world. 16 regional sites in Western Australia were granted access to GMN night sky cameras in 2023, enabling them to provide data. The project's goal is to create a decentralized, high-quality device that can observe the night sky from any location in the world. For the purpose of visualizing meteor trajectories and shower flux, the GMN offers a data dashboard, an Explorer, an SQL/REST API, and other tools. Meteor data from the GMN is viewable on interactive maps under a CC BY 4.0 license. By utilizing a worldwide network of citizen scientists, the GMN advances planetary defense and space science by deepening our understanding of meteors, meteor showers, and the near-Earth meteorite environment, and in order to create a continuous record of meteorological activity, which includes annual meteor showers and outbursts for future studies, and also to build a decentralized worldwide scientific instrument. The GMN uses citizen scientists as hosts to examine the night sky every night of the year from as many locations as feasible. Additionally, the network makes data easily accessible for independent analysis, quality checks, and the usage of open source tools, hence increasing data accessibility and transparency. In order to lower the cost of participation in meteor observing, using low-cost CMOS video cameras and Raspberry Pi computers, the Global Meteor Network aims to make meteor observation more accessible to amateur astronomers and citizen scientists worldwide. And this is what it all comes to, a small group of enthusiasts. You know who is not going to save you? Definitely not Big Protector Jupiter, Man in Black, Jeremy Corbell and George Knapp. No Defenders of the Galaxy, not Bruce Willis, not even Silver Surfer or Starship Troopers will be here to help us. The tiny little speck we call home, a comfortable blue, white, and green world, can only be protected by us. We can only use a tiny little portion of the military budget that is annually spent on mutual destruction to monitor and prepare for a meteor threat. So don't hesitate to participate in the GMN outreach program. Schools can apply for a free camera system or build their own if they want to be a part of a global effort. The project normally starts in September each year depending on funding availability. Come as you are. With the aid of GMN tools, individuals, organizations, or educational institutions can participate independently. When you're ready, you can start, and GMN will make arrangements for you to communicate with other attendees. To get started, go to the GMN registration page and register. To keep informed and interact with other members, sign up for the GMN mailing lists at groups.io. Utilizing low-light video equipment, set up your own Meteor camera and utilize the GMN software to observe the night sky and provide data. This is one of the best affordable projects a citizen scientist can put his paws on, and you know what I say? Science projects are like people you know, and the man and a woman are known for the company they keep, right? So let the meteors be your companions. Stay selective. Bye-bye.